Hi everyone, in this video I want to talk about cyclic sugars, and we're going to focus on the two main biological sugars that you should know a lot about, ribose and glucose. So in prior videos we talked about how we can draw sugars in sort of a straight chain form or the Fischer projection form, which has the open chain aldehyde present. But it turns out that sugars, because of the presence of hydroxyl groups in the same molecule as an aldehyde, they can actually cyclize and form a hemiacetal. So let me draw the structure of ribose, and let's look at how this might form a cyclic sugar. So ribose is actually an aldopentose. So I'm going to draw out the aldehyde here, and we'll draw it in the Fischer projection form. So ribose is pretty easy to remember. It's going to have all of the OHs coming off of these vertical lines going over to the right of your structure. And if I number the carbons, carbon 1, 2, 3, 4, 5. So this is D-ribose. And again, we know it's a D-ribose because if you look at the farthest chiral carbon away, that would be carbon 4, the OH group is on the right-hand side of this vertical line. So this would be called the open chain aldehyde form of ribose. Okay, however, when you put ribose into water, only a small percentage of it actually exists as this open chain form. It's actually going to prefer to exist in its cyclic form. So what I'm going to show you here is that it's actually this OH group on this 4 position. It's going to actually want to cyclize up on the carbon 1 and form a hemiacetal. So before I do that cyclization, what I want to do is I want to rotate this structure 90 degrees. Okay, so I'm going to basically take this and turn it on its side. So put the aldehyde over here, and then I'm going to kind of wrap the chain around it. So let me draw this over here. So this is again carbon 1. This is carbon 2, this is carbon 3, and what I'm doing now is I'm wrapping the rest of this chain sort of around it, so carbon 4 is positioned here, and I'm going to also do a slight bond rotation between carbons 3 and 4 to position this OH group so that it's sitting right next to the aldehyde. And then carbon 5 is out here. So again, carbon 1 is the aldehyde. I've just rotated the whole thing 90 degrees. And I'm sort of wrapping the chain around, putting my hydrogen there, and positioning the OH coming off carbon 4 so that it's sitting right here next to the aldehyde. And when I do that, the CH2OH of carbon 5 is now sort of sticking up. To help visualize this, let's just make these bonds a little bit darker. And that gives it a little bit more three-dimensionality. So carbons 2 and 3 are sort of sticking out towards you. So what can happen now is the OH group can actually cyclize onto the aldehyde, and it can do so in one of two possible pathways. Okay, I'm going to call this pathway on top, we're going to call that A. If the OH group attacks this aldehyde from sort of the top face of the aldehyde, notice what will happen is this oxygen will have to flip in a downward direction. So this is a reversible process. Let's go ahead and draw what that would look like here. So to start out, just draw your 5-membered ring. We're going to sort of make these bonds in front a little darker. And then I'm just going to put vertical lines coming off each of the carbon positions. So again, if I was going through pathway A, this oxygen attaches to carbon number 1, and the OH group at carbon 1 would have to be flipped downwards. The rest of the molecule is going to be exactly the same. So I can put OH and OH there, hydrogens up top, and CH2OH here. So then this is carbon 1, 2, 3, 4, and 5. Okay, so when the OH group at the carbon that's now been attacked by the alcohol of carbon 4, when this OH group is sitting below the plane defined by the ring, this is called alpha D-ribose. And just to introduce a little terminology, when we do this cyclization, the aldehyde carbon in its cyclic form is now a hemiacetal, and we also call that an anomeric carbon. So carbon number 1 in this form is called the anomeric carbon. So I've drawn what's called the alpha anomer. Okay, it's kind of like the word enantiomer, but it's called an anomer because, as we'll see, it's only going to differ in the other structure we're going to draw at the position of the OH at carbon number 1. So again, this was the attack on the top side. If I do the attack on this aldehyde from underneath the plane defined by the aldehyde, we'll call that pathway B. And the only difference is going to be now the OH, or the oxygen on carbon 1, is going to have to flip in an upwards direction. So again, let me draw my 5-membered ring and put in sort of my darkened bonds here. We'll put our lines straight up and down. But now at carbon 1, my OH is going to be up relative to the plane of the ring. The rest of the ring is exactly the same. Okay, and now notice this top one was called the alpha anomer because the OH is below the plane of the ring. Here I now have what's called the beta anomer. So this is beta D ribose. Okay, the OH is above the plane of the ring. You could also look at it in the following way. The exocyclic CH2 group of ribose, notice it's on the same face in the beta anomer, whereas in the alpha anomer, the OH at carbon 1 and this exocyclic CH2 are on opposite sides defined by the ring. So when you look at ribose, this again may exist about, not 10%, closer to 1 to 2% of the time in the open chain aldehyde form. These two forms predominate, the actual cyclic forms. Turns out this one's approximately 60%, this one's approximately 40%. Turns out the alpha anomer is a little bit more stable than the beta. So when you actually were to look at the structure of ribose in solution, the dominant forms are these cyclic hemiacetals. All right, in the next section, we'll see how glucose can do a very similar type of reaction. So what I'd like to show you now is how glucose can actually form a cyclic sugar as well. So we've drawn now the Fischer projection of D-glucose. This is carbon 1, 2, 3, 4, 5, 6. So when we look at glucose, the OH group that's going to actually want to cyclize is actually the one at carbon 5. It's going to end up cyclizing on the aldehyde carbon 1. So like we did with ribose, what we're going to have to do is rotate 90 degrees. So I'm going to take this structure and imagine flipping it down. I'm then going to wrap the chain sort of around to position this OH group next to the aldehyde. In doing that, I'll also do a slight bond rotation around carbon 4 and 5. So let's draw this out over here. So here's my aldehyde. And when I do that, I get a structure that's going to look sort of like this. So notice this is again carbon 1. When I rotate this 90 degrees, the OH at carbon 2 is now going to be sticking down relative to the plane defined by these atoms, and the hydrogen would be up. Notice carbon 3 alternates, so this OH is going to be up, hydrogen down. Carbon 4 alternates as well, OH down, hydrogen up. And because I did this slight rotation between carbons 4 and 5 to position the OH near the aldehyde, I have a hydrogen going down and then CH2 OH. This is carbon 5, this is carbon 6, 4, 3, 2, and then 1. Okay, so I've now positioned the OH coming off carbon 5 next to the aldehyde. Just like we saw with ribose now, this alcohol could attack either from the top face, we'll call it alpha, or from beta, or from the lower face, which ultimately is going to lead to either the alpha or beta sugars. Okay, so if I go through pathway A, my structure now will look like this. Let's focus just on the anomeric carbon to start, then we'll fill out the rest. So if pathway A is occurring, the OH is coming in from the top side of the aldehyde, so this oxygen will flip down relative to the plane defined by the new ring. Conversely, if it goes from the underside of this, the oxygen on carbon 1 is going to flip up, and I would then get the OH up relative to the plane defined by the ring. Now let's go ahead and we'll fill in the rest of our structure here. So going back up to this one, we just have to put our little vertical lines. The rest of the molecule is exactly the same as I drew it before. This is carbon 1, 2, 3, 4, 5, and then we have our exocyclic CH2OH. So this top one now, because I have the OH below the plane of the ring, this would be called alpha D-glucose. Likewise down here, if I fill in the rest of my molecule, all of these would be the same as the previous structure. Oops, that's an OH up top, sorry. And this would be beta D-glucose. And like we saw before with ribose, the open chain aldehyde form 1 to 2% in terms of the actual presence of that in solution. The alpha anomer is a little bit more stable. It's about 55%. This one's about 45%. So the alpha in general for both ribose and glucose is a little bit more stable. Now notice that these are reversible reactions here. So if I had pure beta D-glucose and put it into water, after a few minutes, this would open back up to its open chain form, recyclize, and then equilibrate between the two. That process is called anomerization. Okay, so I'm basically going between the two anomers. These two are related as what are called anomers. Okay, the alpha anomer and the beta anomer of D-glucose, they only differ in the location of that OH at carbon number 1. All the rest of the molecule would be the same. Okay, so glucose and ribose, two extremely important sugars that we'll be talking about a lot more in our class. You probably want to go ahead and memorize the Fisher projections of both ribose and glucose, as well as how to be able to draw both the alpha and beta anomers of both. All right, I hope that helps with cyclic sugars. Definitely get some more practice drawing these, and good luck.